Hey everyone, welcome back to the AI Research Roundup. I'm Alex. It's May 4th, 2025. Okay, today we're looking at an ICLR conference paper published just over 3 months ago. Accelerated Training Through Iterative Gradient Propagation Along the Residual Path. This paper introduces Highway BP, a way to speed up training deep sequential models like ResNets or Transformers. It approximates backpropagation iteratively and in parallel, really leveraging those residual connections for faster computation. Alright, so this figure really helps visualize the core idea. It shows a typical residual layer, forward and backward passes. But the key part is circa. It illustrates how the total gradient is actually the sum of gradients flowing through all possible paths. Highway BP approximates this iteratively. For k equals 0, it's just the pure residual path shown in blue. Then k equals 1 adds paths through one block, and so on. This k controls the approximation level. Building on that approximation idea, this next table shows how the authors actually decompose the layers in common models. We see examples like ResNets, Transformers, GRUs, LSTMs, and how each layer function f_i is split. It's broken into an expensive block, g_i, and a computationally cheap residual connection, r_i. This specific decomposition is crucial. It's what allows Highway BP to efficiently parallelize the gradient calculation using those cheaper residual paths. Okay, moving to the results. This figure plots the final performance for various models like ResNets, GPT-2, and Roberta. The red line represents Highway BP's performance based on the number of iterations compared to standard backpropagation shown by the black dashed line. What's really striking is how quickly Highway BP converges to the standard performance, often needing only a few iterations, like k equals 4 for a deep ResNet. This demonstrates the practical effectiveness of the approximation. Okay, and this figure really drives home the speed advantage. It plots validation loss against wall clock runtime for a GRU. Standard backprop is the black line. Slower. Highway BP, shown in color for k equals 0 up to 3, achieves similar or better final loss, but in significantly less time. Look how much faster the red line, k equals 3, finishes compared to black. It really highlights the practical speedups, often 2x or more. So to quantify those speedups we saw, especially for RNNs, this table lays it out clearly. It shows the speedup factor of Highway BP compared to standard backpropagation for models like LSTMs and GRUs, with different sequence lengths, L, and iterations k. Look at k equals 0. We're seeing around a 3x speedup. Even with more iterations like k equals 5, it's still nearly 2x faster. It really quantifies the acceleration, particularly for longer sequences like that last GRU example. Okay, so complementing the speedup numbers for RNNs, this plot shows the final performance for LSTMs and GRUs against the number of iterations, k. We see Highway BP in red, standard backprop as the dashed black line, and a fixed point baseline in blue. Look how quickly the red line converges towards the black line's performance, often needing just k equals 2 or 3 iterations. It also consistently outperforms that fixed point method, reinforcing that the speedups don't sacrifice much accuracy. Alright, building on that performance analysis, this next figure dives deeper into how the Highway BP approximation itself converges during training. The top plots show cosine similarity to the true gradient. You see it rapidly approaches 1.0 with just a few iterations k. The bottom plots show the contribution of each step, which diminishes quickly. The colors, blue to red, indicate training progress, suggesting perhaps more iterations might be beneficial later on for the closest approximation. So wrapping things up, we've seen how Highway BP cleverly exploits residual connections to significantly accelerate training through parallelization. The big picture is that this method offers impressive speedups, especially for RNNs, often 2 to 3x faster, while maintaining performance close to standard backpropagation with just a handful of iterations. A really promising approach. Well, that's our AI Research Roundup for today. Thanks for joining me. I'm Alex.